MFGE 321, Metrology, Thread Gauges, in depth. So, welcome to the online lecture covering thread gauges. I call this in depth, but in all honesty, there are volumes written on bolted fasteners, as well as reams and reams of standards covering threads, thread forms, torque tension requirements, etc. This lecture will give us just an overview of the metrology of thread measurement, and I'm giving the extra gravy here because this is very testable information, if you catch my hint. The book covers in some detail all of these gauges, but we'll focus here on thread gauges, thread plug gauges, as well as a bit on thread ring gauges. Thread plug gauges are very similar to plain plug gauges. The most obvious difference is where we would see a gauge pin sticking out of the ends of a gauge handle while we see a threaded shaft. Thread plug gauges are specified at the high and low limits of size of the pitch diameter. Shorthand for pitch diameter is PD. And we'll talk about this and what that is in a moment. The gauge is the reverse replica of the thread form being checked. For a thread plug gauge, it mimics a threaded bolt or stud and allows the user to check an internally threaded part, like a nut. In this way, checking the thread form with a solid thread gauge determines assemblability with a mating part. Pictured here are typical thread plug gauges. One of most interest of this lecture is the double-ended thread plug gauge, set up as a go, no-go gauge. In the left-hand pop-up, we see here a nut ID thread being checked with a thread plug gauge. In the right hand of the pop-up, we see a tapered pipe thread wherein the depth of the mating thread part is checked. So all go, no-go thread plug gauges check 4 conditions. These 4 conditions are highly testable material, hint, hint, so make sure you understand this. And I will help you with the following slides in this online presentation. So, number 1, go thread plug gauge will not screw into a hole. That means the pitch diameter, the PD, is too small. It's undersized. The go thread plug gauge will screw into the hole. It means the pitch diameter is within the low limit of the thread tolerance. It's good so far. Now, the no-go thread plug gauge will not screw into the hole. Okay, pitch diameter is within the high limit of the thread tolerance. Good as well. And then if a no-go thread plug gauge screws into the threaded hole, well, then the pitch diameter is too large. Pitch diameter, also sometimes known more properly as the mean diameter, is the the mathematical average diameter of the major and minor diameters as shown in the figure. Note in the figure, the roots and crests come to sharp points, and these are ideal sharp points, and they are ideal for mathematically calculating the mean diameter. The flank angle is the included angle between the thread faces. It is the mirror image of the thread angle. Now the pop-up shows a very different reality. This is how threads really look once they are formed as produced from a thread rolling operation. You can see the roots or base of the thread, known as the minor diameter, is very much more rounded and varied. The same can be said for the crests that make up the major diameter, again rounded and varied. The thread pitch is defined as the axial distance between a point on the thread corresponding to the same point on an adjacent thread. Manufacturing variation aside, the dimensioning and tolerancing of thread form is based upon the ideal. Gauges, however, will check reality. All the same stuff applies for internal thread. One important aspect is the minor diameter of internally threaded parts. I'll talk more about its importance in a moment, but I just want to make sure we're all on the same page as to what a minor thread diameter is for an internally threaded part. Take a nut. No, not a walnut, not a peanut. There it is, a machine nut. The minor diameter is the largest pin you can slip into the nut. Diagrammatically, it is that pin that just appeared on the drawing to the left. That is the minor diameter of a nut. It is the smallest internal diameter. Make sure you can identify it from the drawing. Threaded plug gauges do not check that diameter. They're designed to allow clearance between the minor diameter of the nut and the minor diameter of the thread gauge. So, how do you check the minor diameter of a nut? With a pin gauge. And I'll go through that example in a bit. Now, the major diameter of this internal threaded design here is the largest diameter cut by the threading operation, and it is listed on the diagram as well. Thread plug gauges check the pitch diameter, max and min, and verify the major diameter of the thread is not undersized. We'll learn in a few moments that this is called checking the maximum material condition. So let's take a guided tour through a thread plug gauge. You ready? Hang on. Okay, so for imperial or USCS threads, that's the US standard type stuff, right? Typical are UNC and UNF. UNC, Unified National Coarse, and UNF, Unified National Fine. There's also BSW, British Standard Whitworth, not the BS you were thinking, and BSF, British Standard Fine. Now, pitch is expressed in numbers of threads per inch. For example, quarter 20, UNC. You've probably heard people say, "Hand me that quarter 20, would you?" Well, the 20 piece being 20 threads per inch, or 20 TPI. Now, for metric threads, the pitch is a single thread measured and expressed in millimeters. Example, in M10 by 1.5. The 1.5 is 1.5 millimeters, and that means from the same point on two adjacent threads, the distance is 1.5 millimeters. Now, the gauge you see here, there's the product description of it. It's a left-handed, because you see the LH here, which is a bit rare, taper lock, double end, thread plug gauge set. It's a go, no-go with a handle. It is serialized and traceable through a 17025 accredited lab. The gauge size, quarter inch, threads per inch 20. It's a series UNC class 2B. The go length is half an inch, the no-go length is 5/16. The go pitch diameter is 0.2175. The no-go pitch diameter is 0.2223 inches. And the material is tool steel to a Rockwell C of 60 to 62. And it's a Class X tolerance gauge. It's a pretty nice gauge. So that's how you describe in grave detail a thread gauge. Now, formed threads can have faults. They're going to have many faults. And here are some examples of geometry faults. External threads will be checked with thread ring gauges and not thread plug gauges, but in the drawing here it's way easier to depict the thread geometry faults with external threads. But the same thing applies either way. The top sketch on the left depicts the thread pitch desired. You can see the lower two sketches, the thread pitch and the short thread, the long and short thread pitch, they're out of whack, right? Both of these failures will be detected by a thread gauge. The sketch on the right shows a thread form that might in fact have the desired pitch as well as the desired diameter, pitch diameter. Yet, because of its distorted shape, the errors in the flank angle would fail a thread gauge. This is a feature of any functional gauge. Functional gauges check to seek and uncover if parts will be interchangeable and function in an assembly. A threaded part with a large enough flank angle error will fail the functional thread gauge check for interchangeability. So functional fits, functional gauging, functional contact, right? Thread fit is a combination of allowances and tolerances to measure that, to measure the tightness or looseness between a nut and a bolt. A clearance fit is one that provides free running assembly. It's your standard spin the nut on the stud, spin the nut on the bolt thing, right? An interference fit is different, right? There's a positive interference or some kind of frictional component requiring tools for the initial rundown of the nut. Those are, typically lock nuts or prevailing torque nuts. Okay, for this lecture and for our class, we're going to focus mainly on, we'll come really pretty much entirely on, focusing on free running fits, things that go together without a prevailing torque. Now for unified in-screw threads, there are 6 standard classes of fit that afford different levels of allowance or fit. The B sort of section, 1B, 2B, 3B, those are for internal threads. There's three more now, 1A, 2A, 3A. Those are for external threads. And we'll cover this in a bit more detail, but they're all considered clearance fits. That is, they assemble without interference. However, the higher the class number, the tighter the fit, but they still run freely. Shown here is a typical graphical depiction of thread class fits. So let's kind of deconstruct this graph a bit. The black graph bars reflect the range of pitch diameter max and min for each class of nut. Nuts are internally threaded components. The gray graph bars reflect the range of pitch diameters max and min for each class of bolt, an externally threaded component. Putting these two bars together depicts the interchangeability range of a particular class of fit. So note that class 1A, 1B, and class 2A, 2B have an allowance at max material condition. That's smallest hole, biggest shaft. We'll talk about that in a bit. The thing is, there's an allowance, there's a gap there, right? There's an open space between the bottom of the one bar and the top of the other. This makes for easy assembly for limit parts. Class 3A, 3B, that's a line-to-line fit. That allows for no thread allowance. We'll explain why that is in a minute, but you can see it's a very much tighter fit. So now specifically for class 1A, 1B fits, note the range of the pitch diameter for each part. That's the length of the bars represents the range of the allowable pitch diameter size. 1A, 1B are hardware store, muffler shop sort of stuff, right? Not super high strength or high load, and we'll talk about that in a moment. However, this class is suited for quick assembly, easy disassembly, right? Outside of low carbon threaded rod or muffler clamps, this thread is rarely specified in engineering solutions. When we think of bolted joints, we think of strength. Hardware store 1A, 1B type fits are not the first choice that should come to mind when you need a strong, reliable joint. And here's why. It turns out that thread clearance, that is the fit between nut and bolt reflected in the thread class, can have a dramatic impact on joint strength. Somewhere around 70% or more of the strength of a bolted joint comes from the load carrying ability of the first three threads. This is known as thread stress, and the looser your thread tolerance, the more gap you will have between threads. This gap reduces the overlap of the threads from nut to bolt, increasing the thread stress for a given load, which reduces the load carrying ability. The tighter the fit, the more overlap you get. The more thread overlap, the lower the thread stress for a given load, and the greater the load carrying ability for the bolted joint. Many failures in bolted joints have come from improper thread fit specification. Now, bolted thread design is really outside of the scope of our class, but checking to make sure bolts and nuts meet specification through the use of functional metrology is exactly what this class is about. Here in the pop-up, we see the results of thread failure. Now, I can't tell you if this is a result of poor design, or if they chose the wrong class of thread, or if the fastener was manufactured poorly, or if there was a problem with the material itself. However, it is failures like this that get people hurt and get people killed. And it's often why you hear me say, wrong answers don't build bridges. So with that in mind, we step up to the next class of thread fit. It's the 2A, 2B class. As we compare it to 1A, 1B, we see a reduction in the allowable pitch diameter tolerance, which improves thread overlap and in turn reduces thread stress for a given load. We see the same allowance, which preserves a reasonable ease of assembly. 2A, 2B is a good design compromise between strength, cost to manufacture, and ease of assembly. Now, often you will see a dog point stud of some sort, dog points on studs or bolts to help ease assembly, especially when fine thread applications are being chosen in vehicle assembly plants where an operator has to be able to get into a vehicle that's bouncing along an assembly line, use a power torque wrench to get in, cinch a nut down, and get back out. When they got to do a series of fasteners like that. Finally, we have Class 3A and 3B, 3A bolts and 3B nuts. And these are suited for close tolerance requirements. These fasteners are intended for service where safety is a critical design consideration. This class of fit has restrictive tolerances and no allowance. Maybe you'll find socket products, and they'll typically have a 3A, generally have a 3A thread fit. Now, because of a tighter fit, thread form and lead-in the thread geometry is critical. You can see too from the graph, the mating pitch diameters are more closely matched, which provides greater thread overlap and higher strength. With this, however, comes tighter manufacturing tolerances, more inspection, tighter process control, and more headaches for the manufacturing engineer. However, when you have a process that's dialed in, there is certainly a well-earned pride in producing high-quality Class 3A bolts and Class 3B nuts. Now here's a table. The table's in our book, but I included here to help summarize the relationship between thread fit class and their use. We see here outlined in the center of the table the unified screw thread range labeled U. 1A, 1B is our hardware store swag on up through 3A, 3B, which I call rocket scientist hardware. You can also see the comparisons for metric threads and a quick use guide at the bottom of the chart down there. For unified national thread, as the number goes up, the fit gets tighter. A is external thread, B is internal thread. So we talked about threads and specifically UNC thread classes. This is where A is the bolt and B is the nut. And the higher the number, the tighter the thread. So now it's time to actually start using our thread gauges. So how do you do that? Well, the go, no-go thread plug gauge has two ends to it. The go end of the thread plug gauge checks the maximum material condition, the function limit of a threaded part. I'll go into grave detail regarding max material condition, or it's also known as MMC, in our GD&T portion of the class. But a quick primer here is in order. In the pop-up, we see a hole and a pin. Both are dimensioned with a tolerance of plus or minus 0.1 millimeters. Max material simply means, well, maximum meat, if you will. If you want your plate to have the maximum meat, you will want the smallest hole in that plate. In our case, the max material condition MMC hole will be at the dimension nominal 10.2 minus the 0.1, which will yield a 10.1 millimeter hole. Conversely, MMC for a pin is the largest pin, which in this case is nominal 10.0 plus 0.1, which is a 10.1 pin. MMC, max material condition, checks to make sure the largest tolerance pin will always fit the smallest toleranced hole. Maximum meat pin fits maximum meat hole. In this case, it'll be line to line, a perfect fit, provided we have perfect form. Now, verifying the MMC ensures interchangeability of assembly of toleranced mating parts. And this includes the major diameter of a nut thread. For the products to be acceptable, the gauge must enter and freely, this is a thread gauge now, must enter freely and pass through its full threaded length. This is the go side of that gauge, right? Because the go gauge makes a cumulative check of all of the thread elements except the minor diameter, you have to come back and use a go, no-go pin gauge to check to make sure the minor diameter is in spec. And we'll hit that in a bit here in a moment. The no-go end of a thread plug gauge checks the no-go, the high logo, functional diameter limit of the threaded part. It's also known as the least material condition. The pop-up here gives us a quick picture of LMC, or least material condition. I'm not going to go into the math behind it, but the largest hole in the plate means the least material condition. The same for the smallest pin. In the world of fastening, we are verifying the functional diameter limit, and this helps to ensure there is sufficient amount of material for the required operational strength of a fastener or fastened joint. The part being checked is generally acceptable when the no-go threaded plug gauge does not enter more than 1.5 to 3 turns, dependent upon customer specifications. The no-go thread plug gauge has the major diameter truncated. It only tests the pitch diameter and does not check for undersized major diameters. So let's work our way through this thread plug gauge. We see that it is to check a 3/8 inch by 16 threads per inch coarse thread of a class 2B fit. If we dig out our handy dandy UNC thread table, we find the 2B class thread for a 3/8 inch 16 thread, and we see the min and max pitch diameters to be 0.3344 and 0.3401 respectively. And these are reflected on the gauge handle, which I like to see. It's helpful. So all's good there. We see the go side of the thread gauge is long enough to assure we can fully thread the nut onto the gauge with which to check. And we can test to make sure the nut does not pass the no-go side. But this doesn't tell the entire story. If the hole drilled through the nut when it was being made is too large, we will have precious little thread engagement. The functional checks of the thread plug gauge would pass, but because the thread gauge only checks pitch diameter and not minor diameter of the threaded hole, we'll need to look deeper into the thread table data. We see we have min and max minor diameters, so we need to dig out 2 pin gauges. It's important to note the same goes for OD threads in like bolts and studs. And in this case, however, you can use a pair of calipers to verify a major diameter of a bolt or stud. The thread ring gauge that would be used to check the bolt or stud will check MMC, including minor thread diameter of the bolt, but it won't check the major diameter of a bolt. Application time! Okay, now it's time to practice the use of a thread gauge. Well, we'll practice it virtually because this is online, but maybe we'll have some time in class to muck about with it. But here, this is a real example of a specialty engineered nut. And we're going to be checking the thread class, the pitch diameter and thread form of the ID thread, and it's a non-standard minor thread diameter nut due to the 55% thread depth. This means that the engineer can, and here did, modify how much of the thread crest is present in the nut. So we grab our handy dandy 3/8 by 16 UNC class 3B thread gauge and also pull the corresponding thread spec. We check to see if our nut to be checked passes the go and fails the no-go. We thread the nut under the go, and okay, it threads on easily 3 turns and completely engages the nut. Good. Next we try the no-go, and yep, it no-go. So far, so good. Now here's where it gets a little bit tricky, and why it is super important to read the print and pull the associated specs when performing measurements, especially when you are setting up your control plans, which will be the topic of a future lecture. The standard minor diameter callout for a UNC 3/8 16 class 3B threaded nut is a minimum of 0.3070 and a maximum of 0.3182. However, in the print callout, we see a minor thread callout of 0.327 plus or minus 004. This gives us a different number, right? This gives us an MMC of 0.323, which is our minimum allowed through hole, and an LMC of 0.331, which is our maximum allowed through hole. The engineer here is mucking about with the standard thread form. Okay, fine. We know this sets up our needed go, no-go gauge pins to check the minor diameter of our specialty nut. Remember, minor diameters are not checked by thread plug gauges. We must use pin gauges to perform this check. Our next step is to grab some check pins. And use care here because there are plus pins and there are minus pins. We discussed this a bit in class, and it's important that you make sure you compensate for gauge maker's tolerance when selecting your check pins. So in this case, we added gauge tolerance to the MMC pin by selecting a plus pin to increase the pin size and protect the customer, because the hole will always be just a hair larger than allowed by MMC when using a plus pin. And we subtract the gauge tolerance from the LMC pin by selecting a minus pin. And that decreases the size of the pin and protects the customer such that the hole will always be just a hair smaller than using what would be allowed for LMC by using a minus pin. So, if the go pin does not fit, you go to put the go pin in and it doesn't fit, you are absolutely assured that the minor diameter of the thread is too small, which means we exceeded MMC. We got too much meat, hole too small. Conversely, if the no-go pin passes through, then you know the minor thread diameter in the nut is too large. We exceeded LMC. There's not enough meat. The pin went in. In the picture, we see the go pin fits and the no-go pin stops short. We are within the tolerance band for the non-standard minor thread diameter specified. Okay, now folks, make sure you get this. You know, this is really no different from a threaded hole or a non-threaded hole. Review the pin gauge tolerance table in your book. Use this example. Try a class Z pin, run the numbers, and convince yourself of how this works. This is testable stuff, folks, here. Testable, testable. All right? Good. Let's move on. So in summary, the go, no-go thread plug gauge function and the 4 conditions that are checked. So, if the go thread plug gauge will not screw into the hole, then the pitch diameter is too small and not interchangeable at the chosen tolerance, or perhaps the major diameter is also too small. How about this one? If the go thread plug gauge will screw into the hole, then the pitch diameter is within the low limit of the threaded hole tolerance. To check for interchangeability, though, we need to do one more thing. We need to check with a gauge pin. We must use a gauge pin to check the minor internal diameter. How about this one? A no-go thread plug gauge will not screw into a threaded hole. The pitch diameter is within the high limit of a thread plug gauge tolerance, which is good, and it also assures strength of the thread. You don't want it to screw into the hole. If it screws into the hole, something's a problem, right? That's the next question. If the no-go thread gauge does screw into the hole, the pitch diameter is too large. There's likely not enough meat on the threads. So, ring thread gauges pretty much do the same thing as thread plug gauges do, just on OD threads. So, the go side, the thread ring gauge checks again MMC, max material condition, and its functional size. You're looking for the largest pitch diameter per thread tolerance and minor thread diameter. Now, no-go rings, they size for the least material condition. Functional size again, smallest pitch diameter per thread tolerance. Also note how the go thread gauge is thicker with more threads than the no-go. The same principle as the thread plug gauge. The go gauge needs to fully engage the threads, where the no-go gauge simply needs to have enough threads to prove no-go. It's important to remember the OD threads on parts like bolts and studs can be checked. You got to use a pair of calipers to verify the major diameter of the bolt or stud threads. Okay, now lastly, here's an interesting example of how thread plug gauges can be used. It comes from Johnson Gauge in Bloomfield, Connecticut. The threaded plug gauge shown was produced by Johnson Gauge, and they're an ISO 9001 registered company, and they also happen to have an ISO 17025 certified measurement lab. These guys got their act together, right? This is a stepped thread gauge, and it might be kind of hard to see with the YouTube video resolution that you're watching this on, but as we've now learned, the thread plug gauge checks MMC inclusive of the major diameter of a nut or threaded hole. Having a stepped threaded gauge allows the user to independently check for pitch diameter and then pitch diameter plus major diameter. In this case, this gauge is used to set up a variables measurement gauge for measuring OD thread. So here it is. This is a transfer standard, right? It's almost a reference standard, but used to compare a separate standard that Johnson Gauge used when they produced this variables gauge. And it's used to set up and calibrate the gauge before use. These threaded plug gauges are pretty useful things indeed. So there you have it. You've survived another one of my scintillating online how-to videos. Thread gauges in depth. Well, sort of in depth. Look, there is quite a bit of quizzable and, dare I say, testable info here. So you want to make sure you understand this stuff. You know, use the book. I've written the book for a reason. It's in there. This is supposed to be a help. This is not the Cliff Notes. Use the book. Together with the book, the in-class lecture, and bring your questions, and this how-to video, this should give you what you need to have to be successful in employing functional thread plug gauges and thread ring gauges. All right, see you all in class.